Hey, it's Dr. J. Welcome to Calculus. This is the first lesson, Introduction to Limits. So you'll hear me say this a lot if you haven't already heard me say this before, that calculus is 90% algebra. So most of the day-to-day work and the calculations that you'll be seeing me do in this course will be very algebraic in nature, with a splash of geometry in there, but 90% of it is algebra. So what really brings algebra to the next level and creates the study of calculus is the concept of a limit. So in this introduction, I'm going to use a classic algebra problem, that's application problem that you may have seen before, to sort of break the ice and discover the concept of a limit, and then at some point give the formal definition of what we mean and the notation for writing a limit, and finding what the result of the limit is. So my first example is compound interest. And we're going to do what's called fixed rate, fixed term. So if we invest P dollars, it's called the principal, at R% interest, I will just write R, given as a percent, annual interest, for a period of T years. That's called the term, or the period. Then the amount can be determined. So when I say the amount, I mean the amount that you will have at the end of the term. So you can think of this as like a certificate of deposit. It has to be a fixed rate, fixed term, so they don't change it over time. The amount that you will have will be the principal multiplied by 1 plus the rate divided by n to the nt power. So that is your compound interest formula, where n is the compounding frequency. Compounding frequency is a fancy way to say the number of times it's compounded per year. All right. So there we go. That'll be our first example. Let's go ahead and suppose principal is $8,000. Our rate is 3%. And our term, or our period, is 6 years. All right, so I put $8,000 into an investment that's going to guarantee a fixed rate of 3% annual interest over a term of 6 years, or a period of 6 years. Sometimes we call it the period, T, time, term. Okay. Let's explore various compounding frequencies. All right, so to get an idea of how much we will have, well, it depends on how often we're compounding the interest. All right. The most common frequency is monthly. Every month you get a statement. They've compounded the interest once a month, yeah, and then you get a statement, and it sort of keeps you updated as to how fast the money is growing. Let's go ahead and do that. So we got $8,000. 1 plus 3%. There's our 3%. Raised to the n, number of compoundings, times t, 6 years. Now I'm only going to show you this once. I assume that you already know it, but very quickly do this as mental math. This is a calculus course, so you probably do this without even thinking about it. But 3% really means 3 divided by 100. Yeah, percent. And so written as a decimal, that's 0.03. Okay, so whenever we have an application problem where a number is given as a percent, you're going to want to do this quick mental math to turn it into a decimal before you plug it into your formula. I have seen people put the number 3 right there instead of 0.03 or 3%, and it screws everything all up. All right. Okay, so moving right along, n equals 12. What do we got? The amount is $8,000. Now be careful. You know, algebra, order of operations, that 800, you're going to multiply it when you're done with all of the other stuff, okay? So let's put this into our calculator here. We got 3% divided by 12 months. All right, and then go ahead and add the 1 now, plus 1. And then the exponent, I don't need the calculator for that. That's 72, all right? I'm going to keep this base number on my calculator. I'm going to hit the exponent button depending on the type of calculator you have. On this calculator, it says y to the x power. Then I type 72. All right, and I get this multiplier factor, 1.19. What is it? 1.196948. Now, just to make things clean, I'm going to just put the answer over here so I don't use up a lot of my board space. So I'm going to multiply by $8,000. And not too shabby. $9,575. And then you get a trailing decimal, 58774. I want you to round this to the nearest cent. So that's $9,575.59. Okay. There we go. Not too shabby. But your natural instinct, I mean, you might be happy. So yeah, that's great, right? $8,000. You waited 6 years. You waited 6 years to get this money, right? But your natural sort of greed or human instinct is to say, well, what if I want more, right? More, please. Is there any way to increase this amount without increasing the amount of time, right? And the answer is perhaps, yeah. What if we did it every week? What if every Friday or once a week, there are 52 weeks in a year, if we increase the frequency of the compounding, perhaps this dollar amount will grow. And I mean, you can't make time go by faster. 6 years is still going to take 6 years. But perhaps without changing the rate, right? Because the rate is fixed, it's 3%, and the term is fixed, 6 years. The only variable that you have is the n, right? How often you compound. So let's try that and see if we get more money out of it. So this time, we're changing the value of n. So now we've got 52 weeks. We could do the whole thing on our calculator here. So we've got 3% divided by 52 plus 1. Then do the exponent. I don't want to clear my screen in order to do the exponents. Let's see if we can do that mentally. 52 times 6 is 312, if you're not sure. Now, if you clear your screen, you're going to have to do that all over again. I don't know. Let's see. Yep, 312. All right, so we're going to raise that to the 312 power. All right, that's our multiplier factor. In some intuitive sense, that's how much larger that's the product of that times your initial investment, which was $8,000. And we have increased it to $9,577.24 this time. So it did go up a little bit. Yeah. $2, right? $2. Maybe you see where I'm going with this. What can we do after weekly? All right. How about every day? Every day when the bank opens, compound my interest. Tell me how much I've got. All right. So that would be daily. Now, typically we ignore leap year. Okay. One trick I can do here, and I'm going to do it for the rest of the examples. This is about the extent of how much, mental math or, hand math, hand calculation that I want to do. So I already know that it's going to stay 6 years. Right? You see, this happens every time. Right? So I want to go ahead and do that first. Right? So just down here, I'll do a quick scratch. NT is 365 times T. It's 365 times 6. That's going to be 2190. All right, that'll be my power. Just saves me from having to clear out my screen. And I'm not going to go spend $100 on a fancy calculator. I mean, there are fancy calculators if you own one where you can literally just type in this entire formula. I still have the $20, Walmart version. Actually, I bought this one at Walgreens, but nonetheless, it's the cheap drugstore calculator. It works well, I've bought a lot of fancy calculators in my life, and I always end up right back at the simple ones. So I've got my 0.03, 365. I went ahead and did the power in advance, so I know it's going to be 2190. And now I can do all of that on a cheap calculator. So 0.03 divided by 365, then plus 1, all right? Then raise it to the 2190 power. There's my multiplier. It's pretty close to the same number, and then times 8,000. And this time I've got $9,577.67. So I've only increased it by about, by 43 cents. And that's with the rounding. I just did the rounding for you. All right. But I got more money, yeah. It's cents, but it's more money. I'm not going to do this with a larger amount of money in this example, but maybe later I'll act like I've got a lot of money, and I like to fantasize when I'm doing mathematics about, well, what if I had $1 million, right? Or $1 billion, You'll find that the difference between these two numbers, we'll see this later, when you have $1 million is a lot more than 43 cents, but we're only investing $8,000, which might seem like a lot of money but in the grand scheme of things, it's not. Okay, so you can kind of see where I'm going with this. Look, the values are getting larger, but they're not like taking off. I don't think it's ever going to get to 10,000. It's not, right? So the idea, and I'm going to keep doing a few more, is there a limit? And I'm not using the mathematical official definition of a limit. I'm using, sort of just the humanistic version of the word limit. Is there a limit to how high this number will go? And the answer is, of course, yes, there is. So what is it? Well, let's do a few more, all right? Let's do a few more, and maybe we could figure out what that limit is. All right, I've got room for a couple more. What's after daily? How about hourly? Every hour. Now, you might already have this memorized, how many hours are in a year, but I don't. So 365 times 24, there are 8,760 hours in a year. All right, and then I'm also going to go ahead and do my NT, because I know that my T is 6 in all of these, and I like to have that power ready to go. So let's multiply that by 6 now. 52,560. That's going to be my power here. Now you have to be careful because the N goes down here. Yeah, but the NT goes up here to the power. 52,560. Okay, so let's do that. 3% divided by 8760 plus 1, raise it to the power 52,560. That's our multiplier again. Now look, notice that multiplier is pretty close. It's 1.19. The decimals change. We call this the tail of the decimals change, but sort of the head stays the same. Times 8,000. And this time, I'm still stuck at $9,577. This time I got 74 cents. So I'm starting to suspect that it will never get past $9,577, but the pennies might go up. I might get more change. So I'm going to keep going because, I'm greedy. I want every last penny, right? Can I get this up to 99 cents? Maybe I can get it to go over 99 cents and get this to be $9,578. I want to squeeze every last penny out of this. And that's really where the limit is going to appear to us, when we really push it to the limit. All right, hourly. How about every minute? You could say minutely. Minutely or minutely. It just sounds funny. All right. How many out there has seen the musical Rent? Yeah, I just got to sing it one time for you. 525,600 minutes. You probably already have it. That's one way to measure a year, right? My singing is not quite up to the Broadway standards, but 525,600 minutes is the number of minutes in a year. If you don't memorize it, then you can just go back to your 8,760, multiply it by 60, and that'll give you the number of minutes. Okay. Let's go ahead and do our NT, because we know we're going to need that. So we take our 525,600 minutes, and we multiply that by 6, and we get 153,600 is going to be our power. That's going to go up here. I'm going to have to erase this. Maybe I'll save it. Here, I'll save it over here. 957559. I'm saving it off screen. although you can probably see it. There it is right there. So this was monthly. Because I got to erase this. My board's only so big. I could get a larger board, but then my camera would have to be, 10 feet tall. It's already about 5 feet tall as it is right now. So I've got it extended as high as I can get it in this particular studio that I'm in. So $8,000. We're almost there, guys. You're going to see the limit in just a minute. 3% interest. Remember the N now is minutes, 525,600 minutes. And then the power is 3,153,600. How did they ever do this without a calculator? Right? Somebody did. Yeah. All right, so I got 3% divided by 525,600 plus 1, then to the power 3,153,600. And there's my multiplier again. Look, it's still 1.19, right? So we're going to get more into this after I'm going to wrap this up in a second. I've already been going on for a long time, but the 8,000's really not affecting the limit all that much, right? I mean, it's affecting the final result, but the real action is happening here. That's the number that's being limited, right? Now, of course, the 8,000 is constant in all of these, so you multiply it by 8,000. If you change that 8,000, it changes everything, right? So this whole problem has a finite deposit. So I'm going to get 9,577,74 now. I got one. Oh, it's the same. I thought I got an extra penny. I got super excited, right? So that's it. We've reached the limit. Yeah. We've reached the limit. You're not going to get more than that 74 cents. It's never going to round any higher than 74. If you are greedy, even more greedy, you just try to squeeze it one more time. Oh, God, I know I just got to try it. Of course, there are measurements faster than a second for you scientists out there. There's milliseconds and microseconds and what was this one, daily or weekly? I'm writing down the result, 9,577,24. Got to erase that. But for practical purposes, when we're thinking about continuity, right? I mean, that's the way we're going to think about it. Something happened every second, right? But I mean, again, we're living in the 2024 now. Or I don't know what year you're going to watch this video in, but when this video was filmed, it was the year 2024, and even this video is capturing me faster than every second. All right, because every second would not be enough. It'd be really sketchy. But I'm not going there. We're going to stop here, right? I'm not going to go any faster than that. So every second, how many seconds are in a year? I just want to see. Maybe I can get one more penny by doing it every second. If not, then I'm going to call it quits and say that we've reached the limit. So I'm questioning whether or not this is the limit. I think it is. But let's just squeeze it one more time and see what happens. So let's do every second. So we got 525,600 minutes. I memorized that one, but I have never memorized, minutes. I've memorized the minutes, but I've never memorized the seconds. Oh, it's very similar to this. That kind of makes sense because it's a multiple of 6. 31,536,000 seconds. That's another way to measure a year. 31,536,000 seconds. And remember, I also need the NT, so I'm going to multiply that by 6. What am I going to get? Is it 18 billion? 189,216,000. That's going to be my power. 189,216,000. So this is it. This is last squeeze to try to find the limit. 3% still fixed rate. Changing the compounding to 31,536,000 seconds. And I'm raising it to 189,216,000th power. All right, let's see what we get. I have a feeling it's going to be the same number, but let's just do it anyway. 0.03 divided by 31,536,000. Make sure you get the right number of digits. Plus 1 raised to the 189,216,000. And look, it's the same 1.19. And then I'm going to multiply that by 8,000. I got my extra penny. 9577.75. So no. I got my extra penny. I got one more penny by squeezing in an extra time. Yeah. Well, that is the concept of a limit. Now, in order to actually, let's write all this down now, conclude this example. I mean, what I could have done, if I didn't want to give you a 20-minute introduction, I could have just written all these numbers down in advance and presented you with a table. I feel like that would have been kind of boring because it's like, all the story behind all of this would have just been captured by this table. But we're going to be doing a lot of these tables in this course. And so it's good to see the pattern after you've done the work to be able to make a determination as to whether or not you really have reached your limit. Okay, so I mean, this example is essentially done. I'm going to move on to example 2 in just a minute. Just as a sort of a wrap up, I'm going to make a table showing all of the data that we have. And as I mentioned, the rate was fixed, the term was fixed to 6 years, the deposit was fixed at $8,000. The only true variable was the N, right? So the amount that we got was really based on N. N was the only independent variable in this problem. So I'm going to write down all this information, then I'm going to erase it. So for a year, we had 9,577, or so for daily, 1 year daily, it went up to 67 cents. For hourly, 8,760, it went up to 74 cents. So if you don't care about that extra change, unless you're depositing a very, very large amount of money, this was what? Weekly? Weekly was, good enough, right? You got an extra couple bucks by going to weekly. What was minutely? This was hourly. Minutely was 525,600. That got us 9,577.74, and then secondly 31,536,000 got us 9,577.75. So we got that extra penny. So that's the end of that example. So what we're going to do next is we're going to ask ourselves, and this is now, I'm going to start getting into calculus now. This symbol here, we say approaches infinity. So in other words, as n approaches to infinity, what happens to a? Although I'm going to do a different problem now because I want to start a new example. So remember, the number that was actually limited was actually this number here. Yeah, what happens to that number? So example 2. What happens to this number? All right. So this represents 100% interest. Yeah. 100% interest, so I just put 1 up here. And the term is 1 year. Okay. And that'll give us an idea of how this is growing sort of at a maximum possible situation, right? Now, I mean, nobody ever, I shouldn't say nobody, but I mean, 100% interest is very, very rare. Okay. So we call this the limit as n approaches infinity. So here's the symbol for limit, L-I-M. Sometimes we use lowercase, sometimes we use capital. Not really very consistent. And then we take this expression, or this function of n. I'm not using the f of x notation quite yet, but I'll be getting there soon. You can kind of see this is an exponential function. And I'm going to ask myself what happens to it. Yeah, what happens to this? And we're going to notice a similar pattern, right? But the pattern won't be $9,000 because we're not investing, $8,000. I guess you could think that the principal is an invisible 1 out here. So you can think of this as $1. Yeah. Well, I'm not actually going to put a 1 out in front here, but if you don't have a multiplier out in front here, if you don't have the 8,000 that we had in the last example, then this would be $1 at 100% interest for 1 year. That's what this expression represents. All right. So let's go ahead and do various values of n. And this time I'm going to fill out this table here. With new numbers as we go along. I learned my lesson last time. I might as well start keeping track of these as we go. So that I can put my results in here. All right, so let's start with 10. I might want a little bit bigger box over here. Let's round to 4 decimal places. So I'll do 4 decimal places. So around to 4 decimal places. All right, so let's do n equals 10. So what do we got? Now we're just going to hold off on this, and we're going to wait. We can't predict the limit until we plug in a few values of n to sort of look for a pattern here. So we got 1 plus 1/10 to the 10th. This is going to go a lot faster. So we got 1 plus 1/10, which is 1.1 to the 10th power, 2.5934. So 2.5937, right? It keeps going, but I only want the first 4 decimal places. So look at the 5th place and decide if you're going to round it up or down. Okay. All right, let's go to 100. (1.01 to the 100th power). 2.704813829. So 2.7048. I'm going to be erasing a lot of this stuff, so we'll keep this as our record, our bookkeeping here. Give myself a little more space. Let's do 1,000. 1.001 to the 1,000th power. 2.716923932. 2.7169. And let's do 10,000. 1 plus 10,000. I'm going to start just writing decimals here. So that's 0.0001 to the 10,000th power. I start off writing them as fractions, but it starts to get really ridiculous. So I'm just going to switch to decimals. So we're going to raise that to the 10,000th power. 2.718145.927. I'm writing down everything I see on my screen, and then over here I'm going to round it. So that was 10,000 for n, and 2.7181. Again, look at the 5th digit to decide. That's what we call the dictator, to decide if we're rounding up or down. All right, so this one was a 4, so we kept it at 8.1. And I have just enough room to squeeze in the last one. Normally I like to go to 1,000,000, but for this example, we'll stop at 100,000. One neat thing about using the decimals is the pattern is pretty easy to see. Each successive decimal will just have an additional 0. It's the powers of 10 rule. Probably learned that rule when you were a little kid, right? You remember being like, I don't know, 10 or maybe 9 years old, and you learn, 10 times 10, 10 times 10 times 10, and you could always nail those multiplication facts very quickly at a very young age. All right, so we're going up to 100,000, and we'll call it quits. So I've got 4 zeros, and then a 1. That's 1 and 100,000th. And we're raising that to the 100,000 power. And this is going to be as far as we can go for predicting our limit. All right, and then we're going to look at our dictator is the 6. So our limit we are going to predict is 2.7183. So we predict, or we estimate, it's not exact, it's kind of an estimate because we're rounding, the limit as n approaches infinity of 1 plus 1 over n to the n power is equal to, or since I'm estimating it, I'm going to do the squiggle squiggle, approximately 2.7183. That's the estimated limit. It's not the exact limit. The exact value is an irrational number. $2.7182812828. That's as far as I know it. 46. It's an irrational number. This means that it's non-repeating and non-terminating. Kind of like our old friend pi. Yeah, we learned pi in geometry. We might see it appear again in this course. But this number will probably show up a lot more often in this course. This 2.71828. When we round it, we're rounding it to 2.7183 because this number is always a 2. That number is always an 8. So this 8 always rounds that 2 up to a 3 when you're rounding. All right. We call this the approximate value of E. The exact value can only be represented by the symbol. E. So when I say E, the symbol E, that is the exact value of this limit. But the approximate value is 2.7183 if it's rounded to 4 decimal places. If it's rounded to 5 decimal places, then it would be 2.71828. If it was rounded to 6, 7, 8, 9, but no matter how many decimals I put, these are always just approximations of E because you can never actually get the decimal to be exact. So all of the decimal values of this are going to be approximations depending on where you want to cut it off at. All right. Most commonly, we memorize 2.71, right? Just like with pi, you memorized 3.14 many years ago. But then you might start to get a little bit more mature and memorize more digits of it. In a calculus course, 4 digits is typically enough. Okay. So that is the concept of a limit, the introduction to limits. Let's do a few examples. Let's do example 3. Find the exact value of the limit. If we were in the classroom for this course, I would probably say DIY. But since I don't want to pause for that long and walk around the classroom, I'm going to go ahead and answer it right away. The most common variable you'll see in this course is x. Yeah, we sometimes use x, we sometimes use t. In the compound interest formula, we use both t and n, but there was no x in there. But I'm just going to kind of show you a general calculus type question here. Your first real calculus question of the semester. From the beginning, as I've been talking, you can probably see that you already know the answer. I've just switched the variables from n to x. Watch out for the language. This is asking an exact value. The exact value can only be represented by the symbol E. Okay. That one was pretty easy. Yeah, no work. I was just using your memory recall from the previous example. This gives us our next formula. Called compounding, or compounded, I'm going to say compounding continuously. All right. Interest, sorry, I forgot to put the word interest in here. So going back to the first example we did, look how much easier the formula is. Wrote down the wrong letter. It's easy if you write it down correctly. So it's sometimes called the PERT formula. All right. So you take this limit, the one we just discussed extensively, and you insert the result, the E, as the base. So you don't need the parentheses, you don't need the 1 plus 1 over. All of that gets condensed into one nice symbol, E. And this is memorized, I memorize it as the PERT formula. It's the compound continuously. All right. So, example 4. Example 3 was really just a fun fact. I called it an example just because, I wanted you to chalk another one up in your notes. But at this point, you can just call this a fun fact. Yeah. So memorize that fun fact. It will come back later in the course. Let's go ahead and suppose you invest $1 million. That's hard to see, isn't it? There it is. There we go. So $1 million at 100% annual interest for 1 year, compounded continuously. All right. So I call this greedy. Yeah, 100% interest, right? You're probably not going to get that in real life, but also impatient. Yeah, so this is greedy and impatient. I don't want to wait much longer. I don't want to wait any longer than a year, right? But I also am rich, right? Which probably makes sense why I'm greedy and impatient, right? So I want my $1 million. I don't need it for a year. I'm going to put it aside. You're going to pay me back 100% interest, right? This mystical, magical bank somewhere in a faraway land for 1 year. How much money will we have at the end of the year? Well, this formula is very nice, yeah? Look at this, how quick this formula is going to be. It's going to be a lot faster now that we don't have to go through the big table. We don't have to do the trial and error method. One way intuitively to think about compounding continuously, it's faster than every second, right? In the first example I did, we stopped at every second. Well, this is even faster than that, all right? It's even faster than milliseconds and microseconds and every other possible second. So E. Now, interest rate, be careful, as a decimal, that's 100 over 100, which is just 1. Yeah. And then my T is also 1. So here's my R. R is 1, and T is 1. So this is going to be 1 million E. Let's round to the nearest cent. Round to the nearest cent. The exact value is 1 million E. Yeah. So if I asked for the exact amount, it would be 1 million E. But I want actual dollars. I don't want symbolic dollars. So on your calculator, locate your E button. It's usually right above the letter LN. So you got to do E to the first power. All right, and you'll notice that number looks just like the number I showed earlier. 2.718281828, and then I ran out of screen. Multiply that by $1 million. Make sure you get the right number of zeros. And you now have $2,718,281.83 because I'm rounding. Not too shabby. Be careful. I usually remove the commas. Probably shouldn't have spaces in between there either. So 2,718,281. Commas are troublesome. You definitely need the decimal point, but sometimes the computer misreads the comma and it thinks that you're separating two numbers. So it's probably better to avoid the commas. Just don't use them. You can use them when you're writing it out to help you sort of count, blocks of 3. Another reason why commas are troublesome is in many countries around the world, the decimal point is actually a comma. Yeah. So that comma in some countries means the cents follow the comma. So using commas can be troublesome. To make things simple, I'm only going to use what's required, which is the decimal point in this answer. So there you go. That's how much money we have. And this is dollars. All right. Don't put a dollar sign. It'll either have the word, there'll be a prompt with the word dollars, or sometimes the dollar sign is already sort of sitting outside the box like that. All right. So not only is this the introduction to limits, but it's also, if this is your first time taking one of my online courses, a little bit of an introduction to how to answer the questions. Okay. All right, well, moving right along, let's go back and review example 1. So example 5 is a revisit example 1. Did we reach the limit that we predicted? So did we actually reach the limit that we predicted? Okay. I've already erased it, but I think it was what was it? $9,577.74 or something. Or I got to 75 cents, right? Unfortunately, I did already clear my board and I didn't write it down anywhere else. But you probably have it. If not, you can rewind and see if we actually reached the limit. So remember, the P was $8,000. The R was 3%. The T was 6 years. Well, if we want to know whether we actually reached the limit, use the PERT formula. So take the same problem, put in your interest rate and your time, and see if we get the same number that we got by doing it every second. Maybe every second was enough to actually reach the limit. So that's going to be 8,000 e to the 0.18 or 18/100ths. 6 years. 3%. All right, and then we're going to raise e to that power. Aha! There's that number again, 1.19. And then we're going to multiply it by 8,000. Huh. I must have entered something incorrectly earlier, because the answer is still 74 cents. I don't want you to get it wrong, so I'm going to make a correction. So, yes, we did reach the limit and identified a minor error in example 1. All right. In example 1, I had put 75 cents. I must have hit something wrong on my calculator. In example 1, it cannot get to 75 cents because this tells us that the limit is 74 cents. And I'm double checking that. Yep, 738. 738, and I'm rounding it up. So it's rounding to 74. So yes, we did reach the limit, and it gives me the opportunity to go back and correct example 1. So the last part, compounded every second, correction. The correct answer is exactly the same as this answer, 957774. So it's not a 5. All right, I don't know what I did. I kind of sensed it. I don't know if you saw me have a long pause and I thought about redoing it, but I was just happy that we got an extra penny and I got so excited. We never really had that penny. All right, so go back to example 1 and correct the change to be 74 cents, not 75. So the answer is yes, we did in fact reach the limit. We reached the limit by rounding. Okay, so sort of yes, we reached the limit by rounding. All right. We never actually reach the limit because if we don't round the decimals, then you will never reach the actual limit because the decimals just keep going and going and going, and they keep changing, and they're not repeating. So it's like you're chasing this tail, and you never actually hit it. But as soon as you round the values to 74 cents, then you have, in fact, reached your limit. Okay, so that was a long, drawn-out example of how to take a limit. Next, we are going to discuss the definition of a limit. So there's two definitions. The one that we're going to use is what's called the intuitive definition of a limit. All right. The intuitive definition of a limit. The limit as x approaches c I forgot to mention the f. The limit of f of x as x approaches c is L. The limit of f of x as x approaches c is L. And we write lim x arrow c, x approaches c, of the function. So f of x is that expression or that function that we are evaluating, is equal to L. Means that when x is near c, very close to, but not necessarily equal to. So that's what we mean when we say near. When x is near c, or in a neighborhood of c, we say that x is very close to, but not, I'm going to put x back in there. X is very close to, but not necessarily equal to c. Then f of x is very close to, is near L. Okay. So when we say near, we mean very close to, but not necessarily equal to. That's our definition of near. So we may never, sometimes we may never actually achieve our limit. Let's see an example of that. Let me squeeze in here the value of f of x, which is different than the limit. This is the definition of the value. I saw that I have enough space here to put one more definition in. The value of f of x at x equals c is f of c. All right. So I just want to make that clear that these are two different definitions. The definition of the limit is saying as we get close to c, but not necessarily equal to c, we call that the limit. This is called the value. It's also known as AKA evaluating. So evaluating means you are equal to. Not necessarily the same as being near. All right. It's best demonstrated using a diagram. All right. So we've got x, and then we've got y. Y is a function of x. And then we have a graph. Of a function. Doesn't really matter what the function's doing. just some curve. It could be a line. It could be several different shapes that it could possibly be. And then maybe we have a dot down here. I don't know. How about right here? Okay, this dot may or may not actually fill in the hole here. So this is sometimes called a hole. This is sometimes called open. Yeah, just remember algebra, open, and this is closed. Okay. So let's assume that it's a unit scale. So we got 1, 1. That's my way of identifying the scale. I really only need to show you one number on each axis. And then based on that number, you can assume that the rest of the numbers follow the same scale. So 1, 2, 3, 4. It'll get really messy if I label every number. If it becomes necessary to label more than a few numbers, I will. I might label the critical value. So 1, 2, 3, 4, 5. That's not a bad idea. And then the other critical value on the y is 3. So definitely want to label the critical values. Okay, so let's talk a little bit about, this is going to be called example 6, I guess, just so you can have a number for it for your notes. Okay, so in this example, let's use the intuitive definition. And by intuitive, I mean that you don't actually have to do anything to get the answer. You just intuit what we mean by this. Yeah. Might have to slide it over a little bit here. Let's see. Example 6. I love my new magnet boards because I don't have to redraw anything when I screw up. I can just slide everybody over here. Special shout out to Amazon for getting me these in one-day delivery. All right. Now I've got some room to do the problem. All right, so example 6. Using the graph of the function, part A, find the limit. All right, let's do the limit as x approaches 5 of f of x. Okay. And so this is what we mean by a neighborhood. Near x equals 5, right? So it's almost like you're just focusing near x equals 5. So when you are near x equals 5, this is your L. Yeah. So this is your C. 5 is your C. And 3 is your L. And you can see intuitively what we're saying, right? And what I'm saying is that if you are very close to 5, then this graph is very close to 3, right? But there's a hole here, and the hole means not necessarily equal to. Right? It's not equal to 3. It's getting very close to 3. So the limit is 3. Okay. Now, I'm really glad I squeezed in that second definition. I saw this coming. I would have had to go and give you the new definition now, but we already have it. Evaluate f of 5. All right, that's different than taking the limit. Evaluating means look at the function, yeah, and plug in 5, right? So this is your y value, and this looks like -2. Yeah. So this is equal to the y value on the graph. The y value on the graph at 5 is not 3. The y value on the graph at 5 is negative 2. Yeah. So f of 5 is equal to negative 2. All right. That's the value of f of x equals y, or f of x when x equals 5. And that's the basic idea, the intuitive idea of how to calculate a limit. I've really only got time for perhaps one more example in this video. So we will pick up with this in the part 2. Let's see if we've got time for one more. I've already got the graphing board handy. Maybe I'll make a little bit more room for you to see. I don't really need a lot of this lower quadrant here, but I do need a lot of this. So let's do example 7 and put this one in. Check this one off in your notes. Okay. Let's do another example. Example 7. Use the graph to find the limit and evaluate the function. Evaluate the function. It's sometimes we say f of x, sometimes we just say f. Sometimes the full proper name of the function is y equals f of x. You're going to hear me use lots of different functional terminology, again from algebra. The short name is just f. Sort of its other representation is just f of x. And then the full representation of the graph is y equals f of x. And I don't always label the x-axis because it's pretty obvious that that's x. Unless it's not, right? Unless we're using another variable, and then it becomes very important. So here's an interesting function. Sorry, I put the hole in the wrong place. There we go. When the graph just kind of takes off the screen, sometimes I'll put an arrowhead on there. You've seen this before in my other algebra classes, but sometimes I won't. I'll just draw it leaving like that, and that assuming that it goes on forever. Okay. We're going to be seeing a lot of these functions in part 2. So you may challenge yourself to just continue working on the homework, even if you haven't seen part 2 yet, because this basic format is pretty standard, where I draw a graph and then I ask you a bunch of questions about the graph. Eventually, I'll stop drawing the graph for you, and we'll start with a blank graph and have to fill it out together. Let's go ahead and label the critical values. So we got 1, 2, 3, 4, 5, 6. So that's y equals 6. And then 1, 2, 3, 4. That's x equals 4. So let's find the limit as x goes to 4. It wouldn't make sense. Well, I mean, it could make sense, so I won't say that. But typically, the critical value is where the hole or the dot is, or possibly both. Notice there is no dot. There's no solid dot. So we'll get to that in a second. So again, as we get close to 4, so there's your C. C is equal to 4. the limit is L, which is 6. So this is really as fast as you can. It takes me longer to draw the picture than it does for you to find the limit. So you're going to pull these up on your screen. If it helps you to zoom in, sometimes down here there'll be a little zoom thing you can hit. It's like a little magnifying glass or something. You can blow it up and look at it. If you can see it the way it is, then that's great. Boom, as soon as you look at it, you can find the limit. All right. Well, we have a problem here. Yeah. This is actually not the correct answer. Yeah. Because as you get close to C, this side is equal to 6. But this one is -1. And so the L must be one real number. All right, I had you there, didn't I? I was about to say, well, the answer is 6 and have a great day and this lesson is over. Yeah, but it just is not that easy, right? I ended with a twist here. All right. If these agree with each other, if they have the same y value, then the limit exists. Yeah, this limit does not exist. So the symbol for does not exist is DNE. This limit does not exist. All right. L cannot be two different numbers. In my next video, we'll talk a little bit more about how to resolve this by approaching it from the left versus approaching it from the right, and how we get two different results. But in this intuitive definition that I've given of the limit, if there are two different y values corresponding to the same x value, so L must be one real number for each value of C, right? So we've got one value of C, 4, and we've got two values of L, and that can't be true. Yeah. And then part B, evaluate f of 4. Well, similarly, there's no solid dot. Yeah. So it is also DNE. There is no point, yeah, closed, solid, or closed. Those are all different ways of thinking about it. There is no actual point or dot. These are all synonyms. Sometimes we call it a point. Sometimes we call it a dot. Sometimes we call it solid. Sometimes we call it closed, right? There's an open hole. A hole is not a dot. A hole is not a point. So there is no value. The value does not exist. And so DNE does not exist. The answer to both of these is DNE. Because I don't really want to end on a confusion. You know, I said that the answer was 6. I paused. And then I said, well, no, it's not. That was too easy, right? Let me show you what the case must be in order for the limit to exist, so that I can actually end this lesson with a very quick example that matches one from the homework. This also matches one from the homework as well, but there's not really anything to do when the answer is DNE. Find the limit. Why did I erase that? And evaluate the function at x equals -1. And we'll end with a good one. All right, so here's -1. All right, so there's our function, sort of like a curve and a hole and a line. We're going to see a lot of these. I should probably put some arrows, or I can just go right off the screen. It would mean the same thing. Not really super consistent with whether I prefer arrows or just going right off the screen. So the critical value here is -1. The other critical number looks like -3. Make sure 1, 2, 3. Nope, -4. I was looking at the screen. -1, -2, -3, -4 is our other critical number. And let's find the same thing. Same two questions. Now this time we're approaching -1. All right. So this time there's only one hole corresponding to one value of C. There's one value of L. There can only be one L for each C. And so this limit is in fact -4. All right. So I tried to fool you. I hope I didn't cause too much confusion. Now let's go to evaluating, right? I don't want to screw this one up, right? This one's not -4. This one still is DNE. Yeah, it is still DNE. Because there's no solid dot at -1. Yeah. So you look up and down along, and you look for a solid or a closed point or dot. Yeah. And you look. Now, I should say within the range of the function that was given. You could be a real, smart aleck and go, well, how do we know the dot's not way over here, off the screen or something like that? Well, you don't, all right? So you can only answer the question in so much as it is presented in the graph. So based on this graph, it does not exist within this graph. It might exist outside the graph, we don't know, but we can't answer something using a graph that we can't see. Now, what's great about this course and what I'm really excited is as we move forward, we will be able to answer questions about a great many things that we can't see, but we can't do it by looking at the graph. We have to use other methods to find that value if it exists out there. And that's where the real power of calculus and mathematics in general really becomes next level. Okay. So in order for the function to have a value at a point, there must be a solid dot somewhere here. Okay. The best case scenario would be like if the dot was filled in. Yeah. So I should make a note. If the dot was filled in, right, then the limit and the function would match. And that's a topic for a future lecture. This one's already reached its limit. It's sort of virtual classroom time. And so until we see each other again, I'm Dr. Jordan, and I'll see you on the internet.